Yeah, let me know.
Okay, it's recording.
Okay, chance that you can catch up after this.
Yeah.
Okay, great. Okay, we're gonna get started. So this is the penultimate lecture by Chaithanya Shravan about Finetti theorem, and that's a topic that I very much like. So I hope you enjoy this lecture, which I think is going to be pretty good. And I said penultimate because we do have another week where we will have Jalen and myself. And that will be next Wednesday. So,
Okay, thank you. Okay, today me and Shravan are going to talk about Finetti theorem and what does it even mean? Why do people care about it from different perspectives? Hopefully that can overlap with some of your interests. Okay. The story begins quite a bit ago, I think in the 18th century, when people were thinking about probability as a mathematical theory. One of the first things people came up, especially Bayes and Laplace independently, like mid 18th century, was Bayes' rule, which is known to be as Bayes' rule right now. And a typical Bayes' rule looks like this in a textbook. You have some posterior probability on some parameter that you may care to know about, and you have some priors on those parameters, and you make some observations, and you can update your probability from prior to posterior. And a key important point that I want to mention going forward in this is that the priors in Bayes' rule in general take into account a lot of our assumptions, we put in a lot of our assumptions into priors, and that can affect the conclusions that we come at on the other side of the observations after using the Bayes' rule. And one of the big debates since the beginning of probability theory was how do you choose the right prior? What justifies using a right prior over a bad prior, good prior over a bad prior in various forms of assumptions. And Finetti theorem is right along those lines, and we will see why as we go along with the presentations. To talk a bit more concretely, let's take a simple example of flipping a coin. Most of you would have studied various forms of this example in probability theory class, and your task is to determine the bias of a coin. The thing you can do is flip the coin, make observations, use Bayes' rule to estimate the bias. But before going into the mathematical details, to make the point about assumptions, we assume a lot of things when we use the analysis that I showed in the previous slide, which is, and some of the questions that you can ask is, okay, like classical mechanics is all deterministic, and we use this argument quite a few times to say, oh yeah, does that mean that a coin has no bias? Then you can say, okay, you can't know all the information, so that kind of justifies the even use of probability theory here. But
what is determinism have to do with the bias? I mean, if a coin is weighted a certain way, that it will wobble deterministically and come up heads more often than tails with exactly, because it's not weighted properly. What does that have to do with?
So I'm talking about bias as a property of the coin, in the sense that if you know all the initial conditions,
okay,
you can still predict what's going to be the outcome.
All right.
There's nothing unknown there in that sense.
Right.
So if you make the argument that okay, you can't know all the information about it, so how does that justify picking a prior over some other prior? And a lot of the times people say, oh, yeah, just pick the uniform prior. Like that's the most innocent thing that you can do, but you can quickly see that that's not even a good thing to do if your parameter is continuous rather than discrete. where if you have a parameter that scales from 0 to 1, I can skew the scale in such a way that uniform prior on one scale doesn't look like a uniform prior on another scale. So it doesn't make sense to choose uniform prior in those situations. And even worse, what if your observations have correlations? Like if I toss it multiple times and you realize that, oh, like if I have a 0, it's very likely to get a 1 in my next coin flip. Like you can think of it as like a coin with a 1 bit of memory. It remembers what the previous toss was. You can come up with all these like kind of situations. So, but in the previous slide, whenever like the typical experiment goes where you start with a IID prior, where your coin tosses are all uncorrelated and you assume that there is a bias to the coin and you're trying to figure out the bias. But what exactly justifies these prior, IID prior, and even the property of a bias for a coin? Operationally, what does it mean to pick this prior? And this has been a question that a lot of people were trying to understand in 20th century, like around 1930s to till like mid of or late 1900s. Especially Finetti, who's like Wikipedia page says as like a probabilistic statistician or operational statistician. And a lot of the goals in those studies has been to understand probability theory concretely from an operational point of view. And reframing the question, one of the question he was trying to ask is what justifies operationally using an IID prior? And why is this prior? Why am I stressing so much on the prior? Like cares. You can come up with, again, it's simple to come up with a lot of examples where you can show that starting from different priors can lead to different conclusions. For example, like whether you believe that there are correlations between different trials or not, can give rise to different outcomes. Like suppose you have a sequence of observations where you didn't show there wasn't any 1-1 consequently. Does that mean that are the trials correlated? If you believe that, you can come up, you conclude something else. But if you don't believe that, you conclude some other thing. So it's important to start from the good or right prior, because you can end up with different conclusions. But even in this simple case of flipping a coin where you can allow for correlations across observations, you can quickly see that it's not actually possible to keep track of all the correlations, because you can keep flipping the coin how many ever times you want, but how long do you think the coin remembers? Like how long do you keep the correlations? But again, we believe that IID prior is a good prior for this example. So why? And these are the kind of questions that Finetti was thinking about when he was thinking about working on coming up with the operational interpretation for why IID is a good prior. Okay, from a different perspective, say you are trying to understand this whole coin flipping thing from a Bayesian perspective, who's for a Bayesian, all the probabilities exist in their head and it's not part of the real world. And a lot of the times we try to do characterization as a process where we are trying to uncover something unknown, either a bias of a coin or properties of a quantum state. So from a Bayesian perspective, like the question that you can ask is like unknown to who? Like everything has to be someone's, even a probability has to be someone's probability. So whose probability are you trying to find? Say, oh, you can just say I have another friend whose probability that I'm trying to find. Then again, it's not too hard to show that if you introduce another person, you can just like quickly make more complications than questions that you try to solve. And in this scenario, Definity's theorem tries to resolve and give a operational interpretation of the whole process of tomography. And I'm using the word very liberally here, even coin flipping can be seen as a tomography process. Definity's theorem tries to give a operational understanding of this whole process and removes the need for defining what an unknown probability is from a Bayesian perspective. Okay, and like in the case of flipping a coin, for example, like bias of a coin, like biases can't be properties of coins from a Bayesian perspective. Bias is like some observer's property, but Definity theorem in that case, in that example, says, okay, it's okay to assume that it's the property of a coin, even though I don't believe it, but you can proceed as if it's the property of a coin. Okay, I think Shravan is gonna take over here and he's gonna tell us about what exactly is the Definity theorem, and I'll be back to.
You have a bunch of questions.
Yes. Yeah, okay, go ahead.
You just said that bias is not a property of the coin
For a Bayesian.
for a Bayesian. Let's say from a Bayesian perspective, is anything about the probability distribution a property of the thing that you're interacting with?
No.
It's all about your beliefs.
Yeah.
Okay.
Yeah, I just had a simple question, that related to a couple of slides ago. That. I didn't know if you were gonna elaborate on it or not, but was with the uniform distribution for a continuous variable. And how you can weight the scales to make it not look uniform. Could you just elaborate on that?
So suppose like imagine a function which is concave, whose endpoints are 0 and 1. But you made it concave so that it's not x equal to y. A uniform function, like if you take a uniform distribution on x, it's not gonna look uniform on y.
But in terms of like, I guess in terms of like constructing a good prior, if you don't know anything about that, that's like.
Like for example, your model depends on some parameter theta. Or like let's say 3D, like you have a parameter that's in 3D space x, y is coordinate. And you say, okay, like, and yours is, it's in a box and everything is nice. So you can say, I'm gonna start that the particle can be like anywhere, like according to x, y, z. I pick x randomly, y randomly, and z randomly, uniformly. And someone else, a Mohsin will come and say, I don't want to do x, y, z coordinate, I like spherical coordinates. And I say, like r, thetas, and phi's. A uniform distribution on r, theta, and phi is not going to look uniform on x, y, z. So that's what I mean. So you can do these kind of transformations of parameters where uniform distribution on one doesn't look like the uniform distribution on other parameters. So what does it even mean to say that uniform prior is a good prior on which parameter?
But Jeffries solves that problem, right? Prior, Jeffries.
Say that again.
Jeffries prior solves that
Jeffries
problem.
prior.
Yeah, he's saying that the best prior is such that it's variant or some kind of transformation.
Under some particular kind of, does it apply to every kind of model and parameters that you can have, or is it in a specific setting?
Yeah, it depends on the condition of your statistical model. For
Okay.
example, if the quantum information of the parameter is constant,
Okay,
he showed that the flat is a good prior
okay,
because it's invariant with some kind of transformation.
okay, I see.
But it depends on the properties of the statistical model.
I guess another way to put that is, okay, if you, for example, say you want to sample from a sphere, right? You sample, you wouldn't say, okay, it's cos theta, or 2D spheres, cos theta, sin theta, you don't uniformly, you sample from the distribution of cos theta instead of sampling from theta. But if you don't know the underlying structure, right, you didn't know that your sample actually came from a sphere, then how would you decide what is the uniform pair, right? without a priori knowing that you know it's a circle or you have some idea of what is piece of space, the point of what is uniform is really difficult. And I think that's one of the way you can rephrase the point that I was trying to. So great. I will be diving into Finetti's representation theorem. As as Chaithanya already pointed out, there are multiple ways of interpreting what the representation theorem means and what are its implications. But for simplicity's sake, the way I'm going to proceed, at least until I introduce the Finetti theorem, is the Finetti theorem is just an operational way of telling what does it actually mean to assume an IID distribution, right? So before we go to that, I just want to clarify some notations. Here we'll be talking about n trials of discrete binary random variables. That is, each of these variables can take either 0 or 1 values, and this is the probability of obtaining this sequence, pretty standard. And then we'll also be really talking about permutations. We represent standardly, this is just a bijection function, and all it does is re-linearizes. So what motivated me Finetti was, okay, I want to arrive at something that looks like IID, but instead of imposing a math condition on it, can I think about some physical motivation or physical conditions that I must impose on my priors so I get on to the IID? And the first thing that he talked about, that I mentioned, anyways, was the symmetric probability distribution. So symmetric priors are basically priors which are invariant under any permutation. So you have this particular sequence, and then you permute them. It's invariant. The probability of finding that particular sequence is equal to this probability. What it operationally means is that the order of outcomes or trials are irrelevant. So in Finetti's mind, say you do a coin toss now and then you get tails, and then you do a coin toss next time and you get heads. You call this outcome 1 and you call this outcome 2, right? But these 1 and 2 are just your variables. So in Finetti's mind, it was any prior that you choose must reflect that the 1 and 2 are just your choice, and you sort of relabel them. And in some sense, that is why he was thinking about why we need to impose this condition of symmetric probability distribution. Just to hit this point home really hard, let's consider simple example. 2 trials of coin toss, and you have these 4 possible outcomes: head, tails, tails, heads, 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 tails, tails, and the symmetric probability distribution obviously says that this must be the probability of finding this, and this must be equal. Now, what kind of priors actually satisfy this? Obviously, you have your generic IID distribution. This obviously satisfies this, but you also have other kind of distributions which are not IID but satisfy the symmetric probability distribution condition. One is obviously your correlated distribution, where the probability of finding these kind of outcomes are 0. And then again, you can think about anti-correlated distributions, where probability of getting correlated outcomes are 0. So the next question that we can ask is, okay, we have defined a symmetric probability distribution, great. But is this enough? Or is this enough to ensure that the prior that you choose is going to be a conditional IID distribution? Well, I guess if the answer is yes to this, I wouldn't have had this slide. But let me motivate this sort of idea. So the basic idea of prior is you do n trials, and you start with a probability distribution that you believe over the n trials. But there's nothing special about n, right? You could have thought about doing n plus m coin toss, or n plus n plus 1 coin toss, whatever. So to stay consistent, what you would demand is, if you assign a prior for n coin toss, and then you assign another prior for n plus m coin toss, the prior that you had assigned for n coin toss should just be a marginal for the prior for the n plus m coin toss, right? And also, I would want the n plus m prior to also be symmetric, because in that the primal assumption. These 2 points combined is represented here mathematically, and it's known as an exchangeable distribution. So again, an exchangeable distribution is one, which is symmetric. And in addition, for every n greater than 0, you can find a symmetric probability distribution over this n plus n variable such that this prior is just a marginal of this probability distribution, right? And operationally, what does this mean? This is sort of a very hand-wavy language, but the idea is an exchangeable distribution is one where not only does the order of random variables that you choose are irrelevant, but also any additional trials that you might have done, the order of those random variables are also irrelevant. Great. So if I define this exchangeable probability distribution, but are they actually different, or did I just waste your time doing this mental gymnastics? Obviously, all exchangeable distributions are symmetric. What about the reverse? Anyone has any ideas? Well, let's consider the same. Sorry,
You can just cook up a distribution that is symmetric but not exchangeable.
that's exactly what I'm going to do right here. So I'm going to take the two trial anti-correlated distribution, and I'm going to add one more point cost. Right? Since I want it to be anti-correlated in the green and red, these are the 4 possible outcomes with non-zero probability. Right? You erase the blue outcome, you should only see anti-correlated. But now I also want our prior to be exchangeable. What it means is, instead of erasing blue, if I erase green, it must also be anti-correlated. Right? That must immediately cancel those both outcomes. Great. But what about this? What if I erase red? You see that it becomes a correlated kind of distribution and not anti-correlated. So all of this is just to say that anti-correlated distributions are kind of distributions which are symmetric, but they are not exchangeable. So demanding exchangeable is a slightly stronger property, and that is absolutely essential in proving the Finetti's theorem. Right. So yeah, let's jump into this sort of Finetti's representation theorem. I'll just read it on the slide. So suppose we have an exchangeable probability distribution over n binary variables. There exists a unique probability distribution P of Q such that your exchangeable distribution has this particular form. In other words, what it means is, suppose you are given a exchangeable distribution, then there exists a unique probability P of Q such that this can just be thought of as a mixture of Bernoulli independent trials. Right? That's it. That's what this entire thing says. And this n is basically the frequency of one occurring in your sequence. And Q can be interpreted as the probability of getting outcome one. Any questions at this point?
In other words, a bias.
In other words, a bias. So I would actually go through the proof of this, but before that, let's try and understand what this sort of implies, right? At the very first level, no controversy here, is that Finetti's theorem gives you an objective criterion that must be satisfied, under which you can, under which the conditional IID assumption is valid. Or in other words, what it says is, okay, when we do experiments or when we do anything science, we always assume IID, right? And then we go and then we find the mean, we find the variance, whatever. And then now the question here is, when is that assumption actually valid? And Finetti gives you a very practical solution. All he's saying is, you're basically doing a Bayesian kind of update, but you're choosing a prior which is exchange. But here comes the sort of mind-blowing part. Suppose, say you're Bayesian, right? You're going to see that there is no bias. So basically, I can't assign some probability Q, which is which is sort of a property of the coin, which means that you can't really. So it's actually a result of Bayesians not assuming IIDs. So now what this theorem says is, if an agent assumes an exchangeable prior, he can proceed as if there exists an unknown objective probability which he's sort of learning. So in other words, what it means is, if you're not a Bayesian, you're going to assume that there exists a probability Q. You're going to assume IID, and then you're going to do experiments. here you're doing it in the reverse process. You're assuming exchangeability, and the sort of objective unknown probability Q just falls out of the map. Like you don't have to associate it with the coin or as an element of reality. And of course, this is a conditional IID distribution. What that means is you actually do not know what's the value of Q, and the ignorance is captured by this probability distribution P of Q. Now, it also gives you a nice way to think about tomography. What it says is learning is nothing but, so you start with some P of Q, and then you do some measurements, and then you keep updating it. And in principle, what will happen is this P of Q will become sharper and sharper and sharper. And at the point when it becomes a delta function kind of thing, that's when you say, oh, I've learned the existence of this parameter Q, which has this particular value. So in some sense, it gives you an operational description of what tomography is, right? So we just go through the proof because it's pretty simple. Here I'm going to again start with the assumption that our prior is exchangeable. Since we are only worried about binary variables, and since our prior is exchangeable, all we need to worry about is the number of times an outcome has like what you see 1 per 0, and not the exact order of it. Or in other words, all you do is keep count of the frequency. So here I use this particular notation P of small n comma capital N to denote the probability of n ones in capital N number of trials. Again, using exchangeability, pretty simple math, I can show that the probability of this thing is just n choose n times the probability of obtaining one particular sequence, right? Where you get for your first n outcomes, you get 1 and the rest are 0. This thing, you can write it in this form, and that's basically your log of total probability. So what I'm saying is, okay, now think of this capital N number of trials as a subset of a larger number of trials that you the capital N number of trials. And then you can write this using this sort of conditional probability notation, where you can say, okay, the probability of obtaining this sequence is just the probability of obtaining that sequence, conditioned on the number of ones in the larger number of trials times the the probability of that. Simple math. The reason we do that is basically this quantity. So if you look at this quantity and think really, really hard, or just not really, what you can see is this is actually equivalent to drawing this particular situation, which we did, or at least I did a lot when I was in my undergrad, where you have an urn and you have the total number of balls is capital M, the total number of blue balls is small m, and you're just picking out that particular sequence of balls. You have n balls and then n minus n balls. And then the thing is, once you associate this, you know how to calculate probability for that. And then I'm not doing that. When you take m to infinity and you do some nice change of variables, you arrive at the Finetti sphere. That's fine. Great. So far we've been talking about Finetti's theorem for binary variables, but I just wanted to flash this thing and then tell you guys that that's like there is a Finetti theorem for any k outcome random variable. Just that the proof is much more complicated, and why complicate things when we can talk about things in a very simple way. So far we've been talking about probabilities, Bayesianism, and then we've been talking about this Finetti's theorem, which is when do we have an IID kind of situation, blah blah blah. The question here is, can you extend it to a quantum scenario, right? And the answer is pretty simple. So we were working with a classical coin, just quantize the coin, and then now here the goal is, instead of estimating the bias, right, you're estimating the density matrix associated with the coin. This is a very well-known problem in this field, and people know it by quantum state tomography. And basically the assumptions are very simple. In quantum state tomography, you are given a black box which spits out a state, and it spits out the same state each time. So if you have n access to black box, you get a state which looks like this particular thing. And then your idea is do whatever measurement you want and tell me what that particular state is. But now you can ask the same questions that we asked the classical case, right? First of all, why should the black box give me something that looks like this, which sort of is the quantum version of IID, and what is its meaning? When do I operationally see that I can get something like this?
Shravan?
Yeah.
Sorry, what do you mean by quantized Bitcoin?
Oh, that was just a hint to what Merson's talk was, where they were talking about a Wigner's friend scenario where they had a quantum coin. Basically, you can think of it as a qubit.
Okay.
So we have this particular scenario, and then we are asking the same question. So we have this nice Finetti theorem for classical probabilities. Can I use that in some manner and talk about this sort of quantum state probability that people are really interested in? And to do that, the first thing that, at least in my mind, we should do is sort of make the problem very similar to what we have been discussing so far classically, right? So classically, Chaithanya just pointed out that you have a base rule, and then you do this updates again and again, and you have your prior and you have your posterior, and you try to get as sharp as posterior as you can. So this thing is called quantum base rule, but basically the only difference is instead of the parameter that you're trying to estimate, you have the density matrix. So basically, you have a probability distribution over the set of all density matrices, and you start with some prior, depending on who you are. You start with some prior, and then based on your measurement results, you update these priors, and then you get a posterior, and you keep repeating until you're satisfied. Now, because these are density matrices, I can also define this rho prior, which is just the average over the set of all density matrices with this particular prior probability distribution that you've chosen. But I just want to clarify again that what we are doing is we are actually updating this prior probability distribution and not the state itself. The clarity is required because if you go and go and see the literature what a quantum base rule means, this is one thing. John hinted at something which he did not explain. Presumably, it's very difficult.
They use the phrase quantum base rule for several different things. This is just one of them.
This is just
the one we care about.
And also the other point is we are not actually updating the density matrix, we are just updating the sort of prior probability distribution. That's great. So now we have to define two things, right? We have to define what's the symmetric distribution, we have to define what is an exchangeable distribution. A symmetric distribution is sort of very analogous to what we have done, is similar. So a symmetric prior density matrix is something that is invariant under all permutation of n indices. This is sort of the basis independent representation, but you can also talk about it in a basis dependent way where you pick any orthonormal basis, write down your density matrix, and in a sort of basis dependent way, all it amounts to is asking that these coefficients they remain invariant under permutations. We can also define exchangeable prior, which is very analogous to what we did. So we have a symmetric density matrix, and it's called exchangeable because we also want that it is the marginal of a bigger density matrix, which in itself is symmetric, just analogous to what we did classically. You can again give an equivalent basis dependent condition, but who cares? So with all that, we come to this quantum Finetti, which is exactly the same thing. It says that if you have an exchangeable state of n system, it can be uniquely written as this particular form, where the uniqueness comes from this particular distribution, that P of rows distribution is unique. And then the same implications hold true for the quantum case as well. First of all, quantum Finetti theorem gives us an objective criterion under which quantum state tomography is valid. Right? You need, all you're asking is, you're saying that the prior density matrix that you're choosing must be exchangeable. Second, assuming exchangeability, the priors are only reflected on P of O. So basically, if you're assuming that your state is exchangeable, all you're doing is changing this particular probability distribution and nothing else. And quantum state tomography, just like classical tomography, is just making P of rho sharper.
I'm a little bit confused. So the classical deep Finetti theorem looked like IID Bernoulli trials.
Yes.
What does this mean?
So it's sort of similar, right? So basically, as you start out, when you start with quantum state tomography, you assume that you have this rho tensor product n structure because you have a black box and then it just keeps spitting out the same state. You can do measurement of the state, whatever, and then try to extract information about what the state actually is, right? And that is sort of similar to what we do in the classical case. In the classical case, you assume, okay, you have a parameter Q, and then you have this IID distribution, and then you do maybe stuff, you calculate stuff. What quantum definity theorem does, similar to classical definity theorem, is provide an operational meaning to what does it really mean to that particular state. Why? Like this is just a very small set of the states that you can actually have over this sort of Hilbert space, right? H is a product n. You can. Why did you not choose an entangled state? Why did you not choose something? And this is why did you have to choose that particular structure? And that's what quantum definity answers, which is basically if you assume that this thing is symmetric and it's also exchangeable, as I had defined before, you just get back to this particular.
So the bias is the state, right?
Yes.
Yeah, the bias, but that I think the entire point of definite theorem is to discourage you from thinking that there exists a bias or there exists a
Bias in my head.
Exactly. Yes.
Like I think there's like this slight distinction. Because you can have states or like you don't know anything about Bayesian formalism. Like you can think, oh, bias is like a emergent property, but like quantum state is real, like it exists. Here it says that it doesn't matter. Like at the end of the day, you don't see the quantum state, you see outcomes of measurements. So in that sense, you can the definity theorem follows along parallel lines for both the classical case and quantum case.
You know, maybe I can ask her because I'm trying to, remember years ago, this was a big discussion when quantum tomography was our topic. And there's some language that Shravan used and trying to drive the notion of in tomography, you might say you're trying to learn what the state is. But from a Bayesian perspective, the quantum state isn't. The quantum state is your assignment of what you expect to see when you do a measurement. So you can't measure what the state is because the state isn't. So the question is, how does the Finetti theorem get me out of that quandary?
Right. You were going to talk about this, right?
Yeah. I guess just to answer Ivan's line of questioning is, like you. So the Bayesian perspective, states are not real. It's in your head. All you see are measurements.
Probabilities aren't real.
Yeah.
Quantum states aren't there. It's their reflection of what you should assign in your betting problem.
Yeah, exactly. And if you are from that perspective, you could have assigned an entangled prior. You don't know that the state, the black box is spitting out row and row again and again. And you cannot start with that assumption. So how do you even do tomography if you don't start with that assumption? The assumption that you start with is that definitely says, okay, if you don't start with that, you can start with the exchangeable assumption, which is that your measurement outcomes are relabelable. Like you can relabel them and however you want and extend them however long you want. If you assume that, it gets you to the point where you can assume as if there is a state and you can proceed from there. Yes.
Yeah, so I think it's really important to understand that this is beliefs first. So what they're trying to clarify is when does it make sense to act as if there's a quantum state? Right. So if you do happen to believe your experimental situation is exchangeable or approximately exchangeable, as they'll say, then you don't get in trouble by saying okay, basically what I have here is some prior over some quantum statements in this set, right? And then I can do a bunch of experiments, and then in the whole Bayesian worldview, it's not that I do things, collect data, and learn the truth. What I do is I collect data, and that helps me revise my priors, posteriors. And so, in the situation where I've already believed that I think this is exchangeable, that justifies the possibility of having a prior over some parameter in this quantum state. I collect a bunch of data that leads me to sharpen my prior to a very sharp posterior potentially. And then what that just means is, okay, it's not that suddenly quantum states are real. It's just I've become super confident that the best gamble for like the next run of me pressing the button, I should use this quantum state, use Bourne's rule, etc. In that setting.
So it's a justification of assigning a probability to rho. When, I mean, rho is not a thing that can assign a probability to.
It only sort of effectively is meaningful to talk about it being a thing for a particular system if you happen to be in a situation where it's exchangeable. So that is actually sort of like one of the preliminary goals of the experiment. They would say, okay, I need to get myself to a point where I believe pressing this button does the same thing every time, right? And if you don't, then it's not, and then you gotta work harder. Because it's really hard to believe something you don't believe. You can't just say, I believe it, you know, like you believe what you believe. And if you're like Junyi or something, you do a lot of work to make yourself actually believe that your clock is working and stuff like that. So you have to do a lot of work to actually believe that you're in an approximately exchangeable situation. But then once you are, you get all of this goodness and all of these unknown quantum states and so forth.
I think, yeah, like just to drive home that point again, it becomes very apparent when you consider even the classical case. Like you are, what Finetti theorem says is that you can assign a property called as bias to the coin. Coin is a coin, like it doesn't need to have a bias. You just flip it and you get observation. So what does it even mean to say that there is a bias property for the coin? And Finetti theorem says that you make observations and you think that they are exchangeable and you can repeat them however long you want. Then you can assign a property called Q, which pops out of the equation on the right hand side in the equation that Shravan showed. That's called as bias for the coin. It wasn't there to begin with. It was just a bunch of observations with some assumptions, and out of that, the property of bias shows up.
So here bias just means probability.
That Q.
Yeah.
The Q, yeah.
So it's the probability you should say that you're going to get heads versus tails.
Yeah,
That's the bias.
In this case, what we're getting is a parameter which is itself a probability. That doesn't have to be true. So a normal distribution of parameters are mean and standard deviation. Those aren't probability.
Right.
And you could have prior over those though. So there's a subtle difference.
But in this one,
In this one, for the Bernoulli situation, it's a problem.
Q is basically you're determining what probability you should assign to heads versus tails.
Yes. So
Yes.
So, okay, so we have this nice results, Chaithanya and John have been talking about just now we were talking about in detail, we have this one Finetti theorem and a classical Finetti theorem, but here what I'm going to do is how do you actually prove this quantum definite? You have to start all the way from scratch and prove everything, or is there some way, some very nice way which you can use to sort of prove the quantum definity theorem using classical definity. I have to say here that both of them has been done. The first person, like the first people set up the prove quantum definity theorem apparently started from scratch, all sort of math. But the one that I'm going to present here was the work of Caves, Fuchs, and Shack in 2002. And the basic idea is sort of very really interesting here, which is basically noting that the density matrix is basically a probability distribution. It's sort of this, you can always assign some probability distribution that is equivalent to describing the density matrix. And the way to do that is sort of this idea called informationally complete POVM. So what are those? So take any POVM. POVM, the conditions are each of these fx must be positive and they must all sum to identity. And then what you demand in addition to that is that these POBM operators, they span the operator space, the D square dimension space. And if that is true, then we can always write any operator A as
That should have been an A.
oh yeah, sorry. You can write any operator as sigma alpha lambda alpha E alpha times A. And this lambda alpha is just your Hilbert Schmidt inner product trace of E alpha. Right. And so if that A becomes, if your A is your density matrix, then the Hilbert Schmidt inner product actually becomes the probabilities that you calculate out of the POBM. Right. So great. So you need a POBM, and then you you also demand that you have like expands the space of operators. You have expands space of operators. But we're gonna go one step further. We want not only for it to be span the set of operators, but for it to be a minimal spanning set. Or in other words, I want to choose the POBM where these fx form a basis on the Hilbert space. So basically, what happens in that case is you have a one-on-one and onto correspondence between Hermitian operators and the probability space. You can show that any Hermitian operators will give you some probability vector, and for any probability vector, you can also find a unique corresponding Hermitian matrix. And that's basically the proof. So the idea is you choose a minimal informationally complete POBM or weak POBM and collapse the stateful probability distribution. Yes.
Just to give an example, can you give me an example of the informationally complete POBM?
Oh, that is an example in the so basically the idea is it's not a projector, right? Because you have only D.
Is it polys?
No, because you only have D polys. You need so at the very least, if your Hilbert space is D dimension, you need to have a POBM which has D square elements.
So here's a good example. Powering one doesn't work because that will have 6 up, down, left, right, this way, right? You need 4. So just take a regular tetrahedron, inscribe it in the block wall, and shrink it isometrically until it sums to 1. That will be efficient.
Yes, that would be yeah, that's true. So basic idea is okay, choose a make POBM, collapse your state to a probability distribution, and then you apply the classical Finetti theorem, and then you get and then from the classical Finetti theorem, you sort of come back to the operator space using the same one-on-one correspondence, and you get something like these, where these are Hermitian operators, not in general positive symmetry. And there is like one additional proof where you have to show that whenever these are not positive semi-definite, for this to be a consistent density matrix, the probability here corresponding to parts where it's not positive semi-definite must go to 0. And you do that, you're basically proving the quantum definite. I think Chaithanya will talk about some more diffusion stuff.
Yeah, sorry, but what was A sub P in this case?
Sure, yeah. So the idea is you apply the Finetti theorem, right? So you're going to get something like some integral of some probability distribution, which looks like Bernoulli independent line. So from the same correspondence, you take each of those Bernoulli IIDs, and then you can get some operators in the operator space which correspond to those particular probability distribution, right? You have a one-on-one correspondence between the Hermitian matrices and the probability distribution. So that's basically what I'm using, just sort of going back and forth between density matrix space to probability space and then coming back. And that's basically what these APs are. In general, they are just a Hermitian.
One detail is a key in that if you're going to construct a probability simplex where the vertices are minimal informationally complete POBM, like that's what they correspond to, those would be probability 1 for that outcome of minimal informationally complete POBM. The issue is that the so-called state that would give you probability 1 for some minimal informationally complete POBM outcome is not itself going to be positive semi-definite. So, and that's actually true for a whole region. So quantum state space maps to a subset of the simplex. And the point is that probability density could have mass outside of the subset that actually corresponds to quantum state space, this simplex. But it turns out that those necessarily vanish just by existing quantum mechanics, so.
Okay, I guess we already talked a bit about this, the idea of exchangeability and how it justifies the idea of parameters in probability theory in general, and even the quantum case justifies the usage of unknown quantum state in tomography and in other protocols that we use just based on the assumptions of exchangeability. Let's keep talking more about this. So the stuff Shravan talked about, one of the key assumptions is this m going to infinity, that like you have infinite exchangeability. But what if you only have finite exchangeability? Like you don't have all the time in the world to keep doing it forever. You have some finite amount of time and you want to be done by the end of day. And you want to be sure that you're like what you are doing is correct. And like maybe if you had just stayed one more if you just did one more experiment after 5 o'clock, you get new results. Like it shouldn't happen like that. So the way to formalize this is assume that you have n random variables, but you only care up to n random variables, but the exchangeability property holds till n some much larger than n, suppose. Then you can again show that your prior should be as close to IID distribution as possible. That scales inversely with the m, where as long as you can assume that m is like much greater than n, then you're good. And again, this is true for quantum states as well, but here it's a bit more interesting in the sense that if you can think of finite exchangeability for quantum states as some sort of like a monogamy of entanglement, or quantifying the monogamy of entanglement, where if you have symmetric states, it bounds the amount of entanglement that you can have in your system. And this has been a starting point to generalize it and use it in all over the place, all over like quantum literature, where whenever you see a quantum definity theorem, like it goes off rail from this point. And this is the concrete point where it makes sense to talk with classical definity theorem. For example, you can think of exchangeability relative to a subsystem, where you have system A and it's interacting in a symmetric way with a bunch of other systems, and you want to quantify a monogamy of entanglement. Again, you can use tools, very similar tools, to prove definity theorem there as well, and show that if a system is interacting symmetrically with a bunch of other systems, it cannot be entangled a lot with all of them. And it has a lot of other applications, but this is my last slide. I'm just talking here. So one of the people have used definity type theorems to prove capacities for channels, or like for proving approximation bounds for ground states, where you can show that if you can show that entanglement is very low in different circumstances, then you get like tools that you can use to just do whatever you want at that point, basically. Okay, I'm going to stop here. Any questions?
Thank you, guys.